And welcome back. Now we've seen combinational logic circuits and state circuits as the two kinds of circuits we'll look at. So this lecture is going to be about state. The next lecture is going to be about combinational logic circuits. So let's jump right in. Let's first start by trying to build an accumulator. So here's the idea. I've got state circuits. They're used to remember values that we have. We're going to use them for registers, really fast, small and fast. Or memory, which is bigger and a little slower, but still the same idea, same principle, still part of the memory hierarchy. And they're going to help control the flow of information between these combinational logic blocks. So let's see if we can build something without them. Let's actually try to say, I don't need you, Mr. State Circuit. Let's try to build something without them and see what happens. And then we'll realize we kind of need them. So let's jump in. I want to build an accumulator. I want to build, see this loop, this beautiful piece of C code? I want to have, I basically I'm trying to do this. I want to have S is 0. And for I equals 0 to n minus 1, S gets accumulated by the value of x of I. So I've got an array of n numbers, and I add them all up. That's all I'm trying to do. Just simple stuff. It's a one-liner. This is like sum of array, a one-liner in Python, sum of this array. Just sum. That's all I want. I want some array. This is how you're going to do this as a loop. And I want to be able to build a circuit to do that for me. That's the idea. So I want to have x of I coming in, and some sum magic happens, and S is at the output, okay? And by the way, here's how, because we know about signals, we saw the signals lecture before, each x of I is going to be applied in succession, one per cycle. So here's the first one, here's x of 0, here's x of 1, here's x of 2, x sub 2, okay? And after n cycles, in theory, the value is done, and after I've done this n times, S now is holding my output. And it'd be great, actually, if all along S were holding the sum so far. We can call this the sum so far. In fact, S should have been called sum so far for that. Okay, let's try it. Here we go. There's our adder. We saw an adder, just combinational logic, right? We saw a nibble adder before. We saw an n-bit adder, 2 n-bit adders. Here's my adder. I don't even care how many bits wide this is, but you can imagine just single bit. I don't care. So, does this work? I've got come on, this looks pretty good, right? Let's look here. I've got the input coming in. This is my input here. And now the output has to be added, S, right? It has to be added to that somehow. So I like it. This is really good, right? Yeah, not so much. This, by the way, we're going to call feedback. Whenever you have some output feeding back into the input, we call that feedback. Not always bad. Feedback is like a microphone. That's bad feedback, but this is good. We actually use feedback all the time in our circuit. So feedback is fine. This doesn't work, not so much. Number one, how do we control the next iteration? How do we tell this circuit that, okay, now this is x of 0, but then now it's x of 1. How does it even know? It's just like this feedback that goes really fast. And two, how do we initialize it? How do we reset this thing to say, all right, S is 0 initially? Well, no, I can't ever give it because it's always a function of this, whatever it was, and I don't know how to set that. So how do I ever set that line? How do I ever assign a value to this line? I don't even know how to do that. So the two reasons it doesn't work. This is just the naive way. We said we try to go it alone, no state devices, that ain't gonna work. So let's actually introduce a circuit that may work. We're gonna introduce our register. And this is a register that has another input. We didn't talk about this last time. This is going to be a reset line, okay? When that reset line is asserted or goes 1, that's going to reset the register. Well, there's our S equals 0. We reset it initially. And then this is going to be the loader that says, and by the way, this is drawn as the input and the output. Typically things are drawn, signals always go left to right. Okay, unless they're part of the feedback, which you can zip right around. But we're going to assume any block comes in, it either comes in on the left, goes out on the right, or comes in on the top, goes out on the bottom. That's the flow of things. Kind of like how you should play 2048. Down, right, down, right. Okay, that's how that works. So look, we've got this. Here's my loader or clock, okay, which is only on the rising edge of these clocks going to do something. And the rough timing, look, the rough timing is x is going to have its value of x0 over time, and then x1, and remember, that's the vector we talked about, clustering those signals and that, grouping them. And the output roughly is, here's my accumulator. x0 gets initialized somehow, and then it's going to have x0 plus x1. And look at it, it's actually working. x0 plus x1 plus x2. I love this as time goes on. So we're going to actually take a deeper dive into this. This is the last slide here. We're gonna take a deeper dive into actually how this works, but we're really close. This is actually gonna work, and we're really excited about that. We'll see you in the next lecture.